Okay, so we're going to look at an example of a sinusoidal word problem. So a situation that can be modeled by a sinusoidal function, so with a sine or a cosine equation. So we're given that a Ferris wheel is 24 feet in diameter and the bottom is 3 feet off of the ground. So I started drawing the picture here, knowing that the Ferris wheel is 24 feet in diameter. Whoopsies, that's the erase. That means from top to bottom of the Ferris wheel, that's going to be 24 feet. And then the very bottom of the Ferris wheel to the ground is going to be 3 feet. Okay, so if Kenny starts at the bottom of the Ferris wheel, find a cosine equation that will tell how high above the ground he is after t seconds. In order to come up with our cosine equation, let's go ahead and just think about this situation about as time is passing, how high he will be off of the ground as the Ferris wheel is turning around and around. Okay, so we know that the Ferris wheel travels at a rate of 5 revolutions per minute. Okay, so let's think about this. So 5 revolutions per 1 minute. Well, 1 minute is 60 seconds. So that's 5 revolutions every 60 seconds. And if we simplify that fraction, that means that 1 revolution will happen every 12 seconds. Okay. So let's think about this. If he is starting, like he's getting onto the Ferris wheel down here at the bottom, okay, that means after 0 seconds have passed, he will be 3 feet off of the ground. I'm going to call my horizontal axis here time in seconds. And the vertical axis is going to be height in feet. Okay. And the reason I am labeling the horizontal axis as time and the vertical axis as height in feet is because we're being asked to find a cosine equation that will tell how high above the ground he is after t seconds. So height as a function of time, meaning the inputs, the dependent variable is going to be, the independent variable will be time, and we can use t or you can use x, it's up to you. I'll just use x. And then the outputs or the dependent variable is going to be, I'll use y, but y is going to represent the height off of the ground in feet. So after 0 seconds have passed, he is going to be 3 feet off of the ground. Since we know it takes him 12 seconds to complete 1 revolution, and let's say he's going in the, it won't really matter, but let's say he's rotating in the counterclockwise direction. Let's think about this. For him to go from the starting position and then a quarter of a revolution, that's going to take him 3 seconds, right? Because a quarter of a revolution, 12 divided by 4 is 3. So after 3 seconds, he will be, well, it looks, since the diameter is 24 feet, half the diameter, which is the radius, would be 12, but then we also have to take into account that 3 feet. So after he has completed a quarter of a revolution, he will be 15 feet off of the ground. Now it will take him another 3 seconds to go the next quarter of a revolution around, where he'll be at the highest point on the Ferris wheel. So that means 6 seconds total will have passed. And he will be the diameter plus that 3 feet, so 27 feet off of the ground. Okay, and then now he's on his descent. His heights are going to start decreasing. So let's say he goes another quarter of a rotation, so he's back at 15 feet. That's going to be another 3 seconds later, so 9 seconds total will have passed when he'll be back at 15 feet. And then another 3 seconds to complete 1 full revolution, and he'll be back at 3 feet. Okay, so notice our graph looks like a sinusoidal function. Okay, where the midline, the line that cuts the graph in half, would be at 15. To come up with the cosine equation, there are actually infinitely many cosine equations that we could write. But remember, whenever the parent function cosine starts high, so we want to pick a high or a low point to treat as kind of our starting point for cosine. Now, since at 0 seconds, he is at a low point of 3 feet off of the ground, we could think of that as our starting point. So then there would be no horizontal shift for our cosine equation, and we could just think about the vertical shift. The amplitude, so the size of this wave, is going to be half the diameter or the radius of the Ferris wheel, which is 12 feet. Okay, so we'll have y equals to negative 12, because if we're thinking of when x is equal to 0 as our starting point, negative 12 cosine. Now it takes 12 seconds to complete 1 revolution, so we can think about our period as being 12. So if we set 2 pi over b equal to 12 in order to solve for b, that means b would be pi over 6. We don't need to take into account a horizontal shift. There is a vertical shift. Remember, the vertical shift, it's easy to identify what the vertical shift is just by looking at where the midline is, so plus 15. And like I said, that's not the only equation that we could write. Like, let's say we wanted to think of the point 6, 27 as being the point that has been shifted for the parent function. So remember, the parent function, when x is equal to 0, y is equal to 1. So if we think about that point having been shifted, it would be shifted to the right 6 units. So we could write equals negative 12 times cosine of pi over 6, and then x minus 6. Oh, I'm sorry, it's a high point, so we don't need to think about there being a vertical reflection. So 12 times cosine of pi over 6 times x minus 6, and then don't forget the vertical shift, plus 15. Okay, so there are different, you just pick a high or low point to find your cosine equation. Now part B is asking us to come up with a sine equation. Well, our amplitude is the same, right? It's the same graph. Sine normally starts, or sine passes, I shouldn't say start, sine passes through the origin. So sine lies on the midline of the parent function. So I'm going to pick a point on the midline as like my point that was translated from the origin. So I'm going to pick 3, 15, and since the graph goes up from that point, if we're reading the graph from left to right like a book, we would have y equals to 12 times sine of pi over 6, and the graph has been shifted to the right 3, it looks like, x minus 3 plus 15. Now, if we had picked this next point that lies on the midline, where the graph continues to go down from that point, then we could have taken into account a vertical reflection into negative 12 times sine of pi over 6 times x minus 9, and then the plus 15 for the vertical shift. So there are different equations that you could write that would represent the same graph. If we were to graph all 4 of these equations on your calculator, you would see all 4 of the graphs would end up overlapping each other exactly. So it's up to you which one you want to do. It's what you see. Now, to determine how high above the ground Kenny is after these different amount of times, you could just plug in those values, make sure that they are in seconds. So like 27, we could seconds, we could just plug 27 in for x to see what y is, what the height is. If you're using your calculator, you could graph one of these equations. So I'm going to graph negative 12 times cosine of pi over 6. X plus 15. I'm going to adjust the window. Make sure you are in radians. So my window I'm going to have from 0, I'll do like 0 to 24. So it'll represent 2 revolutions. You could just, it's up to you however, I would do at least 1 period. So I'm going to have 2 periods graphed. I'm going to have my x scale go by 1. Y min be 0, Y max be, I'm going to go up to 30. Okay, let's see. So if I'm using my calculator to answer this question, I can go to the table, so hit second graph to go to the table, and then I have this set so that I can just type in values for x. So I'm going to type in 27, and I see, okay, 15 feet off of the ground. I can type in 46, and I see 9 feet off of the ground. And then 1 minute 35 seconds, that's 95 seconds. I type that in, and I get 4.608 feet. And then 1 hour, well, there's 60 seconds in a minute, there's 60 minutes in an hour, so that would be 3,600 seconds. So you would be back at 3 feet after 1 hour if you stayed on the ride for an hour and just kept going around and around and around. To find the first 4 times, Kenny is 19 feet off of the ground. I'm going to go back up here to our graph. So when he's 19 feet off of the ground, let's say it's approximately there. We want to know what these times are, the first 4 times. So we would need 1 more period graphed, which I have on my calculator. We would want to know what those times are for when Kenny would be 19 feet off of the ground. So remember, whenever we were solving exponential and logarithmic equations, first we were solving them graphically, where we kind of decomposed an equation into a system of equations. So we're going to do the same thing here. Really, we're solving for time. So we're being given the value for y. You could think about like setting one of these equations, the y value equal to 19. But you guys don't know how to solve these equations yet. You would probably be able to find the first value, but you might have trouble finding the other value. So we're going to make a system. Sorry, in your calculator, in y sub 1, you could put the negative 12 times cosine, or you pick one of, you could use your sine equation as well. And then in y sub 2, you're going to put 19, and we're going to find the points of intersection. So remember, to find the points of intersection, you're going to hit second and trace. And then number 5 is intersect. And then you're going to move your cursor to the first point of intersection, and it will say first curve question mark. So you'll hit enter. Then it will say second curve question mark, enter again. So you hit enter 3 times, and we get that first time that he will be 19 feet off of the ground is approximately 3.649 seconds. And then we go through that again. Second, trace, intersect, move the cursor to the next point of intersection, enter, enter, enter. And I get, as the second time, 8.351 seconds. And then second trace, intersect again, move the cursor. Enter, enter, enter. I get 15.649 seconds. And enter, enter, enter. I get 20.351 seconds. So those will be the first, oh, it said round to the 100th, and I rounded to the nearest thousand. So those will be the first 4 times that he would be 19 feet off of the ground. We solved graphically using our calculator.